Hello everyone, welcome to this NPTEL course on computational process design. In the last session we have looked at simulation of process flow sheet. What we are going to look at today is we are going to look at different optimization methods used for solving these flow sheet models, or in general the design uh, equations which are obtained in the modeling of the different units. So remember that when we started looking at the linear mass and energy balance, we got hundreds of linear equations for a simple flow sheet, isn't it? So solving these linear equations simultaneously, we require a optimization method like linear programming. And towards the last session, we have seen that several non-linear equations which we get, which we have to solve using a suitable optimization algorithm, typically the Newton's based optimization methods. So clearly the concept of optimization is very important while handling these equations related to different units. So what we are going to see is, we will start with the concept of optimization, then we will look at different non-linear equation solvers, non-linear optimization methods, and then we will move to the linear programming. Then we will look at the mixed integer mixed integer linear programming, integer linear programming, and mixed integer non-linear programming. Some discussion on these lines we will have towards the end of this class, and finally we will see the multi-objective optimization methods. So all these methods can be used for optimization of flow sheets, and also for optimizing the design of different equipments those are present in the flow sheet. So let us start with the concept of optimization. So whenever we are saying that we wanted to optimize any particular function, what it means, it is nothing but what? It is nothing but we wanted to find out what is the point corresponding to the maximum value of that particular function, or minimum value of that particular function, isn't it? So in general, let's say a function ix is there with a decision variable x, and we wanted to optimize this function ix. In that case, what we can do is, we can plot this function ix with respect to x, and this is the point which is corresponding to minima. Similarly, if we plot ix versus x, and we get a point like this, so this particular point is corresponding to the maxima. Very often we wanted to find out such uh, points corresponding to maxima and minima and their corresponding x values. So we can get such optimal point by differentiating this particular function with respect to x and then equating to 0. So you can see that the derivative of this particular function at this point is 0. So we are finding out the derivative of this particular function and then equate to 0, and corresponding to that we find out the value of x, and that value of x corresponds to the optimal solution. So in this case, you can see that in case of minimization problem, again, so see, derivative is 0 both minimization and maximization, but the obtained optimum is corresponding to maxima or minima. That we can find out by taking a second derivative. So in this case, we can take a second derivative, and if the second derivative is positive, in that case the obtained optimum is indeed minimum, whereas when the second derivative is negative, in that case the obtained optimum is indeed maximum. So the necessary condition, if you look at for the optimization, so necessary condition for optimization is the derivative of the function should be 0. So that is what is written at the optimum. And what is the sufficient condition? Sufficient condition is, if the second derivative is greater than 0, then the obtained optimum is minima, and if the second derivative is less than 0, then the obtained optima is the maxima. So this is the necessary, this is the sufficient condition. Okay, again you can see that several interesting design optimization problems we see where we wanted to find out the optimum solution of the decision variables, isn't it? So again, the last slide we have seen only a single variable optimization problem, where the objective function was related to only a single variable. But when we see a real life problem, in a real life problem, typically multiple decision variables are there, isn't it? So in case of multivariable optimization problem, the condition of optimality changes slightly. So in this case, you can see that this is a typical problem of Himmel-Blau function is shown here. You can see that the objective function is function of two variables x1 and x2. So I x1 x2 is given as x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square, and we wanted to minimize this objective function I with respect to x1 and x2. If I plot uh, x1 and x2 and show the different values of objectives, in that case we get a contour plot like this. So you can see that x1 and x2 are plotted against each other, and corresponding to each objective value we are getting one contour here. So you can see that each of these line are having uh, uh, the objective values, different objective values corresponds to the different objective values. So you can see that in this particular problem there are four minimum are present. One is here, another one is here, third one here, and the last fourth one is present here. So there are four minima are present in this problem, isn't it? So now what are the optimization conditions when we look at the multivariable problem? So whenever we are having a multivariable optimization problem, in that case we have to differentiate a particular function with respect to all the variables, and clearly in this case multiple variables are there. So take the uh, we have to take the partial derivative of the objective function with respect to individual variables, and we have to equate that to 0. So that is what is written here. So necessary condition is given as slope of I x1 x2 versus x1 equals to 0, and slope of I x1 x2 versus x2 should be equals to 0 at optimum. So at optimum dou I by dou x1 and dou I by dou x2 both are equals to 0. That is the necessary condition. But when we look at the sufficient condition, so sufficient condition here is based on the Hessian matrix. So Hessian matrix is nothing but it comprises different terms based on the second order derivative. So here if you look at for I x1 x2, the Hessian matrix will be given by del square I x1 x2, and that is given as dou square I dou x1 square, dou square I dou x1 dou x2, dou square I dou x1 dou x2, and the last term here is dou square I dou x2 square. So these are the four terms which are possible in this case. So we can find out all these four double derivatives, and once we get this Hessian matrix, then we have to find out the eigenvalues of this Hessian matrix. So if the eigenvalues of this Hessian matrix are greater than 0, in that case the optimum is minimum. If the eigenvalues of this Hessian matrix are less than 0, then the optimum is maxima. And when some eigenvalues are greater than 0 and some eigenvalues are less than 0, in that case it's a saddle point. Okay, so in this manner we can determine whether the obtained optimum solution is indeed a minimum or maximum, isn't it? So this sufficient condition is slightly more complex in case of multivariable problems compared to the single variable problems, and all these equations we can derive directly from the Taylor series expansion. So in order to understand the concept, let's look at a very simple illustrative example here. So in this case we wanted to optimally design a cylindrical container with radius r and height h to store around 100 pi meter cube of the solution. If the material cost for the top and the bottom surface is let's say 60 rupees per meter square, and that for the side material is 50 rupees per meter square. So you can see that here all these top material which is used at the top and the bottom, the cost of that is 60 rupees per meter square, whereas the cost of the material which is there at this lateral surface area, which is nothing but 50 rupees per meter square. Now in this case the total volume is given as 100 pi meter cube, that is the capacity we wanted to have, isn't it? So in this case total volume 100 pi is given as nothing but what? It will be nothing but pi r square h, isn't it? Where r is the radius of the cylindrical container and h is the height of the cylindrical container. So we can write pi r square h is equals to 100 pi, and this pi will get cancelled out, so we can write down h is equals to 100 by r square. Now since the cost factors are given here, let us calculate the total cost for the cylindrical container. So the total cost can be written as the bottom area into cost factor 1 plus top area into cost factor 1 plus side area into cost factor 2. So in this case, bottom area will be what? This bottom area, remember this is a cylindrical container, so bottom area will be pi r square. So pi r square multiplied by 60, that will be the cost corresponding to the bottom material. For top material, again the area will be pi r square into the cost corresponding to the top area, so that is nothing but 60 again. So pi r square into 60, and this lateral surface area, the side area, that will be nothing but what? 2 pi r h into the cost factor corresponding to it is 50 rupees per meter square. So this entire sum is going to give us the total cost. So we can rearrange this equation. So after rearranging this equation, what we get is this pi r square into 60 and this pi r square into 60, that becomes 120 pi r square, and the remaining here, this 50 multiplied to 2 becomes 100. So 100 into pi r, and h is given by 100 divided by r square, so that is what is represented here. Okay, again we can simplify this equation. So what we get is 120 pi r square plus this 100 multiplied by 100, that becomes 10,000. So 10,000 multiplied by pi by r. So this is the final cost function we are having. Now we wanted to minimize this cost with respect to r, with respect to radius r. We wanted to select the radius r such that this cost becomes minimum. So what we have to do is we have to differentiate this cost with respect to the r, and if you differentiate this c with respect to r, what we are going to get is dc by dr, and we have to equate it to 0. So in this case, dc by dr will be given by this 2 multiplied to here, that becomes 240 into pi r, minus, in this case this 10,000 will remain as it is, and derivative of pi by r will be nothing but what? Minus pi by r square. So that minus sign comes out here, and pi by r square will be here. So this we have to equate to 0. If we equate this to 0, this pi will get cancelled out, and what we are going to get is 240 r is there, and this r square multiplied, so that becomes 240 r cube, and that should be equals to 10,000. So we can calculate the value of r. So r comes out to be, in this case the optimum value of r comes out to be 3.46 meter, and corresponding to that we can put this r into this particular equation, 100 by r square, and we can calculate the optimum value of the height, and that optimum value of the height comes around 8.34 meter. So if we design a cylindrical container with radius of 3.46 meter and height equals to 8.34 meter, that is going to minimize the cost required for the fabrication of this particular cylindrical container. So in this case, again we can cross check whether the obtained optimum solution is indeed minimum or not. So for that, what we have to do is we have to again double differentiate this equation with respect to r. So we will get d square c by dr square, and if we double differentiate this equation with respect to r, what we are going to get is 240 pi r. So derivative of this pi r is going to be just pi, so that becomes 240 pi, and here 10,000 into pi by r square is there. So derivative of pi by r square is nothing but what? 3 into pi by r cube minus 3 into pi by r cube. So that is what is written here. So 3 into 10,000 will remain as it is into pi by r cube. And you can see that if I put the optimum value of r 3.46 is a positive number. If I put this positive number here, you can see that all the terms here are positive. So clearly the double derivative is also going to be positive, and whenever we are having a double derivative positive at the optimum, the obtained optimum is indeed minimum. So clearly we can conclude that the obtained solution here is corresponding to the minimum. So with this discussion, let us now define the optimization formulation in a generalized manner. So whenever we are defining the optimization formulation, first we have to decide on objective functions. So what are the objective functions which we wanted to optimize? In a flow sheet optimization problem, typically the objective function is what? Typically the objective function is to minimize the cost. Another objective could be to maximize the profit. Another objective we can have is to maximize the sustainability index, isn't it? So all these are the objectives we can use in the flow sheet design, and these objectives can be optimized by using different optimization methods. So in this case, all these objectives can be represented in a generalized form like this. This could be maximization or minimization. So we can represent all these objectives as I1, I2, I3, etc. And these are functions of decision variables. In this case, these decision variables we have represented as x1, x2 all the way to xn, isn't it? In a real process flow sheet, these decision variables could be other, like this can be a the fraction of the purge which we are calculating, isn't it? How much is the fraction for the splitter unit, how much is the fraction in the distillation unit, all these fractions can be variables here, isn't it? Even the design variables can also be a variables here, like the volume of the reactor, isn't it? And we will see one example along the similar line later. Okay, so in addition to these objective functions, so in this case I have shown m number of such objective functions, I1, I2, all the way to Im. In addition to this, there will be some constants. So there are two types of constants possible. One is the inequality constants. So inequality constants are nothing but what? These are nothing but the additional conditions which the optimization or a simulation need to satisfy, isn't it? And these are the constant based on environmental regulation, design specification, product specification, safety aspects of the process, isn't it? So all these constants are represented, uh, all these requirements are represented through constants, and this could be inequality constants and this could be equality constants. So when I am saying inequality constants, these are nothing but what? These are the equations which are kind of greater than equals to 0 or less than equals to 0 of type. So you can see that there is no equality sign here, it's a inequality here. So there are j number of inequality constants are there, and we are representing that all these j constants are greater than 0. They are represented like this. Okay, and when I am having the equality constants are hk are given equals to 0, and here you can see that k is varying as 1, 2, 3 all the way to capital K. So there are capital K number of equality constants are there, and all these equality and inequality constants should be function of the variables, decision variables x1, x2 all the way to xn. You can see that one more important point to note down here is this equality constants, number of equality constants should be less than n. Let's say if all these equality constants are equals to n, what it means? It means that we have k number of equality constants and there are k variables. That means the system is completely defined, so we will have a unique solution. So if we have a unique solution, there is no optimization required. So optimization is present only and only if there are large number of solutions possible, and out of those large number of solutions we wanted to select the best solution, isn't it? So clearly for the optimization problem, this capital K should be less than n. In addition to these constants, additionally there are bounds. Now what are the bounds? Bounds are nothing but the ranges of these decision variables which we have to specify. These ranges are specified based on the operational practices, what are the ranges of different variables based on the safety perspective, isn't it? So these are selected based on the given operative ranges of the variables. Now you can see that typically when we have a single objective optimization, in a single objective optimization we typically get one optimal solution. Okay, but whenever we are having multiple objectives, like let's say if you are having one objective which is maximizing the customer satisfaction and another objective is, let's say, maximization of the profit. So both the objectives are maximization and both these objectives has to be satisfied simultaneously. Whenever such multiple objectives are there, instead of getting a single solution, we get a set of multiple equally good solutions like this, and all these equally good solutions we refer these as Pareto optimal solutions. So we will see more details on these as we go ahead, and one has to select one of the operating solution out of these equally good solution in the plant. Now whenever we are having multivariable problem, typically there are different optimization methods are there, and these are based on either derivative or non-derivative. So whenever we are looking at the methods which are based on the derivative, these are referred as multivariable gradient based methods, isn't it? Their convergence speed is higher, but then these methods sometimes can stuck into the local optimum. So that is the drawback. In comparison with that, there are different class of methods which are called as non-derivative based method. These are typically the search based method. These methods do not require derivative at all. So they calculate the function values, and based on these function values they make the decision what should be the new optimum point. Okay, and they do not calculate the derivative of the function. Okay, both these methods have their pros and cons. So non-derivative based methods are slow in convergence, but then these methods do not get stuck into the local optimum. That is the advantage. Okay, so both these type of methodologies are used commonly in designing the processes. But if you look at the process flow sheet optimization, typically people use the gradient based method because of their convergence speed. Okay, so if you look at large number of these process simulation softwares, these are based on the gradient based methods. Okay, so we will be looking at some commonly used gradient based methods, and then we will move to the linear programming. So in this case, you can see that when we are looking at the multivariable gradient based methods, these methods require the first or higher order derivatives of the function to direct the search. All methods used in this class commonly use the following search pattern. So you can see that all these derivative based methods, they use a generalized form like this, where xk plus 1 is nothing but the new optimal guess which we have obtained at k plus 1th iteration. We calculate that based on the optimal guess we had at the current iteration, which is nothing but the kth iteration, plus alpha k is nothing but the learning rate or a step size at the kth iteration into sxk. Sxk is nothing but the search direction. Okay, so you can see that the search direction and alpha k, all these terms which are there on the right hand side, these are calculated at kth iteration, and based on that we predict what will be the optimal guess in the k plus 1th iteration. Okay, so in this case you can see that xk is the current estimate of the optimum x star, where x star is nothing but the global optimum which we are looking at. Xk plus 1 is the new estimate, alpha k is the step size or we call it as a learning rate, and sxk is the search direction of the kth step. One more thing to note down here is all these variables which are shown by bold letters, these bold letters are nothing but vectors. So when I am saying x, this x is including all decision variables x1, x2, x3 all the way to xn, isn't it? And all these decision variables I am calculating at k plus 1th iteration. So all these decision variables we have clubbed in this single vector which is shown by a capital letter X. So in again in different methods, so this is the generalized form, but if you look at different methods which are used in multivariable optimization, gradient based optimization, the only difference these methods are having is in terms of how they are using alpha k and sxk. So in some method you will see that alpha k value is used as 1. In some method sxk is based on this first order derivative. In some method the sxk is based on the second order derivative. So you can see that alpha k and sxk are calculated differently in different methods. What is the advantage with respect to this gradient based method? The advantage is they have a higher speed of conversion. Again, the speed of convergence is extremely crucial factor while optimizing the large size problems. So in large size problems you have a limited computational budget available with you, and within that computational budget, computational resources available with you. Within those computational resources you have to optimize your process. In such cases, if your optimization method is having a higher speed of convergence, you can get the optimum solution in less number of iterations. The most popular derivative based methods used are gradient descent and Newton's method. So these two methods which we are going to look at little bit in more detail. You can see that all the bold letters used here in this equation are nothing but vectors. These are nothing but xk is nothing but the column matrix which is given as x1, x2 all the way to xn, and sxk is nothing but the directions and direction which is with respect to each of these variables. So these are given as s1, s2 all the way to sn at kth iteration. Now let's look at gradient descent. So gradient descent, this particular methodology is inspired from the flow of water from the mountain. Okay, so let's say if you go to a mountain trekking and you reach to a mountain top and then you lost your way. There is a large number of trees are there and you are not able to find out the way out. In that case, how you are going to reach to the valley? The best heuristics in such cases is to follow the direction of water. So water is going to flow in a downward direction. So clearly if you follow the water direction, eventually you will be reaching to the valley. So same concept is numerically simulated in the gradient descent algorithm. So heuristics of water flowing from the mountain top to valley is mathematically simulated in gradient descent for solving the minimization problem. This can be derived using a first order Taylor series expansion of the function. So this is the first order Taylor series expansion of the function I xk plus 1. So we know the values of the function at xk. So right hand side all these values are known. Now we have written I xk plus 1. I xk plus 1 is nothing but the point at xk plus 1, and xk plus 1 is the small excursion around xk, isn't it? So in that case we can write down a Taylor series expansion as ixk plus 1 will be given as ixk plus del ixk into xk plus 1 minus xk, and this summation goes all the way to higher order terms. Let's say if we ignore all these higher order terms and only this first order term we have uh, uh, kept here. So in this case, remember ixk is what? Ixk is the value of the function at kth iteration, isn't it, based on the optimum guess we have obtained at kth iteration, isn't it? And since we are interested in minimizing, so clearly ixk plus 1 should be lower than ixk, isn't it? When we are moving from kth iteration to k plus 1th iteration, clearly ixk plus 1 should be lower than ixk, isn't it? Correct. So if I get ixk plus 1 lower than ixk only and only if this second term becomes negative, isn't it? And it becomes more negative, lower will be the ixk plus 1, isn't it? So clearly the lower value of del ixk is the most preferred here, isn't it? So this del ixk is used as a direction here. So negative of del ixk is used as a direction here, isn't it? And if this direction we are putting it in the original equation here, you can see that xk plus 1 is given as xk minus del ixk del uh, uh, xk into alpha k. So what we are going to get is we are going to get the expression for the gradient descent. So that is what we have obtained. So in this case you can see that this alpha k is a step size. Alpha k is a step size, isn't it? And this step size is varying. So see, we can find out this alpha k value optimally in each iteration, or we can use a fixed value of alpha k. When we are using a fixed value of alpha k, in that case we will be requiring more number of iterations, isn't it? Because the same fixed value of alpha k we have used in every iteration. But if we are using a optimum value of alpha k, we need to find out this optimum value of alpha k in each iteration, and therefore one more additional step of optimization is required in each iteration when we are obtaining the optimum value of alpha k. And for that what we do is we optimize a function ixk plus 1 with respect to with respect to alpha k. So we are finding out the derivative dixk plus 1 by dak equals to 0, and based on that we find out alpha k here. So you can see that this particular expression we can put it in the I, and then we optimize this I function I with respect to alpha k, and we find out the optimum value of alpha k. So clearly this additional optimization step is required, and therefore in practice, most of the practical application we use the optimum step size instead of obtaining, we use the fixed step size alpha k instead of obtaining the optimum step size. Okay, so this is what the commonly used practice. Now in this case again pictorially it is shown. So see, you can see that we can start with the initial point here, then we find out the derivative. So del I is nothing but what? Del I xk is nothing but the derivative of function I with respect to different x, x1, x2, x3 all the way to xn. So del I xk is nothing but the column matrix which has the terms like dou I by dou x1, dou I by dou x2, dou I by dou x3, etc. all the way to dou I by dou xn. So that will be the column matrix, isn't it? So we are finding the derivative at this point, and that derivative is giving me the direction, isn't it? So then I am following the direction of the derivative with the step size of alpha. I am reaching to a new point, and at this point again I find out a new derivative. Again I continue along the derivative, isn't it, for the step size alpha. Then I reach to a new point. Again I find out the derivative here. So you can see that eventually with this method we reach to the optimum solution. So this we have shown in a plot where we are plotting ix versus x, isn't it? So these are single variable things which I have shown. But whenever we are having a multiple variables, we have to show these in a contour plot. So this is the contour plot which is shown here. You can see that x2 and x1 is plotted here, and with respect to different objective values we get different contours. So we are starting from this point, isn't it? Then move along the lower value contour with the step size alpha. As we reach to this particular point, if we go beyond it, the function value is degrading. So clearly this is the optimum value of alpha. Here again we are going to find out the new direction, and along the new direction we are again going to continue. So this is what is shown here. See, we are following the direction of the descent till we reach to the deadlock here. If I continue from this point, my function is going to increase. Then again from this, at this point I am going to find out a new direction. I will continue along this direction as long as there is a descent happening. But as soon as I reach here, remember after this point there is no descent occurring here, there is a climbing is there, isn't it? So ascent is happening here, isn't it? So at this particular point again I am going to change the direction along the descent. I will reach to this point, again I will continue along the direction of descent till I reach the valley. So this is the concept used in a gradient descent. Now let's move to the another method, which is a Newton's method. So in the Newton's method we use a second order derivative. So second order Taylor series expansion we use. So if you look at it, follows the such direction of slope of the slope curve till zero line. I will explain this what I am saying here. This can be derived using a second order Taylor series expansion of the function, isn't it? So typical function, how the function is varying with respect to x for a minimization problem is shown here. You can see that for a minimization problem the function is going to decrease and then it is going to increase, and this is the point at which I am getting the minimum, isn't it? If I plot the derivative of this particular function with respect to x, I will get a curve like this. You can see that here I have plotted a derivative with respect to x, isn't it? And this is the optimum point, isn't it? So you can see that Newton's method follow the such direction based on the derivative. So you can see that this is the derivative I have obtained at the starting point. Then I am following the direction of the derivative till I reach to the zero line here. So this is the optimum solution which I have obtained in the first iteration. Corresponding to that, I will calculate again the value of x here, isn't it? Value of first derivative, and clearly this derivative is not zero here. So I will again follow the direction. I will reach here. I will reach to the second optimum point, which is the obtained after the second iteration. Again I will reach to the new point. Again I will follow a new slope here, and I will continue till I reach to this point. So you can see that Newton's method follow the direction based on the derivative, and again you can see that the starting point is very important here. Okay, so let's say if I have a function, let's say like this, and if I start somewhere at this particular point, instead of bracketing this optimum solution, it will diverge along this direction. You can see, isn't it? So starting point is very important in a Newton's method, isn't it? So if you select a starting point which is not reasonable, in that case you may diverge also, isn't it? So as I said, this Newton's method we can derive based on the second order Taylor series expansion. So this is the second order Taylor series expansion. Here you can see that ixk plus 1 is represented as ixk plus del I xk transpose into xk plus 1 minus xk plus 1 by 2 xk plus 1 minus xk transpose del square ixk into xk plus 1 minus xk, and all the higher order terms are neglected here. So now in this case you can see that in this particular case, if you look at, this is the Hessian matrix we are having. Del square ixk is nothing but the Hessian matrix. So it comprises of second order derivative terms. Del ixk is the gradient matrix. So this involves the first order derivatives, isn't it? Now what we are interested in, we wanted to get this new objective function should be new objective value should be corresponding to the optimum, isn't it? So ixk plus 1 should be optimum. So when I am saying that ixk plus 1 is the optimum point, what it means? It means that the derivative of ixk plus 1 with respect to xk plus 1 should be equal to 0, isn't it? So if I differentiate this equation with respect to xk plus 1, what I am going to get? I am going to get, so derivative of ixk with respect to xk plus 1, there is no xk plus 1 here. The variable is xk. Xk and xk plus 1 are different variables. So you can see that derivative of Ixk with respect to xk plus 1 will be 0. Derivative of this first term is having the xk, so this is a constant term. Derivative of the second term with respect to xk plus 1 will be just 1 because of this term, isn't it? So we will have del I xk, that's it. How about this term? Here we have written it in a matrix notation, but actually it is what? It is nothing but 1 by 2 xk plus 1 minus xk whole square. Remember, this term and this term is multiplied, it's a square term, isn't it? So what will be the derivative? Remember, this particular term is constant in with respect to xk plus 1, isn't it? So if you differentiate this last term, since there is a square term here, that 2 will come out, and 1 by 2 1 and 2 that will get cancelled out. So we will have xk plus 1 minus xk, and this constant term will remain as it is. So that is what we are getting, del square I xk into xk plus 1 minus xk, and this entire differentiation should be equals to 0. So we can rearrange this term. If we rearrange this term, what we get is this xk plus 1 comes out to be xk minus del square xk inverse. So inverse of the Hessian matrix multiplied by gradient matrix del I xk. So this is what the final expression of the Hessian final expression of the Newton's method. You can see that this particular expression, if we compare with the generalized expression, you can see that Sxk is nothing but what? Sxk is nothing but the inverse of Hessian matrix into the gradient matrix, and alpha k is just 1. So that is what is written here. You can see that this entire term is Sxk, whereas alpha k, which is nothing but the learning rate or a step size, in this case in a Newton's method the learning rate or a step size is just 1. Okay, so and this entire term is nothing but Sxk. Now in this particular expression, let's say if you put that inverse of the Hessian matrix, let's say if you put as alpha k is just a scalar value, then this particular expression becomes a gradient descent. Okay, so you can see that this particular expression can be even represented for a gradient descent when the inverse of the Hessian matrix, we are taking it as a constant value. As alpha k. So del square Ixk is nothing but the Hessian matrix, and Hessian matrix we are taking as 1 by alpha k in case of gradient descent. Okay. So the same thing is written. The procedure here is like this. In a gradient descent, we start with the initial point x naught, which will be having the x1, x2, all these decision variables at the initial condition. This a user has to specify. Then we are finding the first derivative dou I by dou x1 all the way to dou I by dou xn at this initial condition. So that becomes the gradient matrix. Then this gradient matrix is multiplied to alpha naught, which is nothing but the step size, and we are subtracting from x naught, that gives me x1, isn't it? So again we calculate, we choose the alpha naught such that Ix1 is minimum, or we can select the fixed user defined value of alpha when we are using the fixed learning rate or a fixed step size. Once we get the x1, this x1 will be used in the next iteration, and in this manner we are going to continue multiple iterations till we get these gradient values equals to 0, isn't it? Whenever these gradient values become 0, that's an indication that you have reached close to the optimum. So next method is a Newton's method. In the Newton's method also we start with the initial guess values. Guess values of all the variables are x1, x2, xn, and these are given at the 0th condition. Then we calculate the gradient dou I by dou x1, dou I by dou x2, dou I by dou xn, and then again we calculate the we are calculating the Hessian matrix. So Hessian matrix in this case will be what? Dou square I by dou x1 square, dou square I by dou x1 dou x2, dou square I by dou x1 dou x3, all the way to dou square I by dou x1 dou xn, isn't it? Similarly here the last term will be dou square I by dou xn square. So all these Hessian matrix, this is n cross n Hessian matrix. When you are having two variables, you get 2 cross 2 Hessian matrix. This Hessian matrix we have to calculate at the 0th condition, and then we can find out the inverse of this matrix. This inverse of this matrix is multiplied to the gradient matrix, and that gives me the direction. Once we get this direction is subtracted from the initial solution x naught, that gives us the new solution x1. So clearly you can see that once we get this x1 will be used in the next iteration, and we have to continue for multiple iteration till we get the optimum solution. Now advantage with respect to the Newton's method is what? You can see that this second order Taylor series expansion, it is including the second order terms and all other higher order terms are neglected. So whenever we are having the objective function which is quadratic in nature, all such objective function, you can see that this Newton's method is going to give you the optimum solution in one step, in one iteration. You can see that you can get the optimum solution in one iteration whenever you are having the quadratic objective function. Typically when we are looking at minimizing the error, etc., so minimizing the square of the error is what? It's a quadratic term. So whenever we are having the objective function which is quadratic in nature, we are going to get the optimum solution in one step, primarily because we are using the quadratic approximation of the Taylor series. We are retaining the solution up to second order approximation. All other higher order terms we have neglected. So clearly a quadratic term is there. What will be the second derivative of the quadratic term? It will be a constant value, isn't it? So that is why whenever I am having the objective function which is quadratic in nature, we don't require these higher order terms at all, because higher order derivatives are not possible for the quadratic objective function, and therefore these higher order terms which we have neglected in a Newton's method it doesn't matter, primarily because there is no higher order terms present when the function is quadratic. Now let's look at one solved example. So in this particular case, we are looking at minimizing x1 square plus 2x2 square with the initial point 2 2 using gradient descent, and we are trying to look at this step size of 0.2, and x1 x2 are varying between -5 to 5. So you can see that the gradient descent is starting from one initial guess values, and as we undergo different iteration, we eventually reach to the global optimum solution. Again, we can see this objective function in a 3D plot where x1, x2 and I is plotted here. So you can see that how the plane of this particular objective function is varying. So this is the point where we are getting the optimum, isn't it? Correct. Whereas you can see that x1 and x2 are varying here in this particular plane, and objective function is varying in a vertical direction. So the same problem here we have. So these are solved using the simulation package, whereas if we solve the same problem manually, let us look at how the manual solution we will get. So let's say the same objective function, the initial point is 2 2, and we wanted to carry out the optimization using gradient descent with a step size of 0.2. So this is the objective function. I is given as x1 square plus 2x2 square. We have to find out the derivative of this particular function. So dou I by dou x1 and dou I by dou x2 comes out to be 2x1 and 4x2. I can find out dou I by dou x1 and dou I by dou x2 at the initial point 2 2. So we can put these initial values of x1 and x2 here. So dou I by dou x1 comes out to be 4 and dou I by dou x2 comes out to be 8. Then we can put these gradient values in this gradient descent equation. So xk plus 1 is given as xk minus alpha k del I xk. So this xk plus 1, remember this bold letter is nothing but the vector, isn't it? So it is nothing but x1 x2 at the first iteration. We can calculate that from x1 x2 which is present at the initial given condition. So x1 x2 0 minus alpha into dou I by dou x1 into dou I by dou x2. So this is the gradient matrix which is multiplied to the step size. So you can put all these values here. So 2 will be the initial values, then minus 0.2 into 4.8, and that after simplification what we get is 1.2 and 0.4. In the second iteration, whatever the solution which we have obtained in the first iteration will be used as a starting solution. So we have to find out these gradients at this starting solution x1. So this comes out to be dou I by dou x1 comes out to be 2.4 and dou I by dou x2 comes out to be 1.6. So again we can, in the second iteration, x1 and x2 at the second iteration is given as x1 x2 with respect to the first iteration minus alpha into dou I by dou x1 and dou I by dou x2. We can put all the values here. So after putting all these values here, so x1 x2 at the first iteration we have obtained 1.2 and 0.4, that is what is written here. Alpha step size we are using as a fixed value of 0.2, so 0.2 is multiplied here, multiplied by this gradient matrix. So gradient matrix in this case comes out to be 2.4 and 1.6. That is what we have written here. We can solve this matrix equation. So that becomes 0.72 and 0.08. So after second iteration, this is what the optimum solution we have obtained. You can see that the analytically also we can solve this particular equation just to check whether the obtained solution is optimum or not. You can see that in this case this objective function is very simple, and that is why we can solve it analytically. But when we are looking at the complex process flow sheet, we have large number of non-linear equations. We will not be able to get the analytical solution, and in such cases we have to rely only on numerical optimization methods, isn't it? So that is what we are looking at in the gradient descent as well as in Newton's method. So we can, however, we can compare this obtained solution with the analytical solution. So you can see that the analytical solution is 0, 0. We can obtain the analytical solution as 0, 0. So the another point to discuss here is selecting the step size is a crucial here. Higher value may lead to a oscillations around the optimum point, and the low value takes a large number of iterations to reach the optimum. So you can see that in this case 0.2 we have selected. If I select a higher value of a step size, in that case I will have the oscillations even if I reach to the global optimum. And if I use a very small value of step size, in that case I am going to take large number of iterations to reach to the global optimum. So clearly selecting the step size judiciously is very important. In fact, large number of modifications of these gradient based methods are developed, in which the step size is also automatically modified. You don't have to specify, you have to specify only the starting value, and later as you go ahead, the step size values are modified accordingly. A typical example is if you look at the Adam optimizer, RMS Prof, even AdaGrad. These are the commonly used optimizers in machine learning. They use the same concept. They are based on the gradient descent. However, the step size is step size is modified with a programmed manner. Now let us solve the same problem by using a Newton's method. So in a Newton's method, remember, we require a gradient matrix as well as we require a Hessian matrix. So gradient can be obtained as dou by dou x1, dou by dou x2, isn't it? And the components of the Hessian matrix will be what? Dou square I by dou x1 square, dou square I by dou x1 dou x2, and the third component is, the last component is going to be dou square I by dou x2 square. So we can put the initial values of the variable x1, x2, 2, 2 in this all first order and second order derivatives. So you can see that dou I by dou x1, which is given as 2x1, we can obtain that equals to 4. Dou I by dou x2, 4x2, so that comes out to be 8. Whereas dou square I by dou x1 square, that comes out to be 2 directly, isn't it? If I double differentiate, I am going to get only 2. The double derivative of function I with respect to dou x1 dou x2 is 0. Again, double derivative of function I with respect to x2, that comes out to be 4. So this component of the Hessian matrix we have directly obtained. Now we can represent these components of the Hessian matrix in the Hessian matrix itself. So you can see that we can put all these components here. That becomes 2, 0, 0, 4. And now we have to find out the inverse of this Hessian matrix. So if you find out the inverse of this Hessian matrix, that comes out to be 1 by 2, 0, 0 and 1 by 4. This is what we get. And we can multiply this inverse of Hessian matrix to the gradient matrix, which is nothing but 4 and 8, and that we are subtracting from the initial value of x1 and x2, and that gives me the new value of x1 and x2 at the iteration number 1, and you can see that we are getting the values equals to 0, 0 directly. So you can see that in this particular case, the same global optimum solution we have obtained in one iteration. Why? Because our objective function is quadratic in nature. You can see that all the terms are x1 square and x2 square. Our objective function is quadratic. Remember, I said that Newton's method can give you the optimum of quadratic function in one iteration, and that is why we are getting the optimum solution in one iteration. We don't require a second iteration at all. Now global optimum solution is obtained in one step since the function is quadratic. Often finding the inverse of the Hessian matrix is difficult. Sometimes the method diverges. These are the limitations of the Newton's method. You can see that we need to find out the inverse of the Hessian matrix. Very often when you are dealing with large number of variables, your Hessian matrix may become singular. and whenever the matrix is singular, inverse is not possible. So you will not be able to find out the inverse of the Hessian matrix, and in such cases applying the Newton's method is not easy. Again, sometimes the method diverges depending on what initial solution you are looking at, isn't it? Now let's move to the another important aspect. So see, so far we were looking at unconstrained optimization problem, but when you look at the real process applications in a flowsheet optimization, typically we have large number of constraints present, and all these constraints has to be satisfied, isn't it? So in a unconstrained optimization problem, if you take a two variable optimization problem, this is the typical optimum solution we are getting when no constraint is there. But let's say if I am having a additional constraint which is shown by a straight line here, you can see that anything above this particular line is infeasible. So clearly my optimum solution is this, which is shown by a blue colored circle here, not this red one. So, and such constraints are readily present in a process application, isn't it? So whenever we are optimizing the process flow sheet, or whenever we are optimizing the particular unit, typically we involve large number of constraints, and all these constraints has to be satisfied in the optimization methodology itself, and therefore handling the constraint is extremely important. In order to handle these constraints, there are different methods. Okay, so the popular methods are variable elimination, then the another popular method is a Lagrange multiplier, Kuhn-Tucker substitution, and the last one is a penalty function. You can see that variable elimination, Lagrange multiplier, and Kuhn-Tucker substitution, these three methods are referred as mathematical substitution. So what these methods do, they convert your unconstrained they convert your constraint optimization problem to a unconstrained optimization problem. So whatever the constraint you might be having, they will be mathematically include these constraints in the objective function itself, and therefore your constraint optimization problem will be converted to a unconstrained optimization problem, and this unconstrained optimization problem then you can solve using the different solvers which are based on the Newton's method or a gradient descent method. The last method is a penalty function. In a penalty function method, instead of doing a mathematical substitution, we calculate the objective function, we also calculate the constants, and whenever there are constant violation, we are going to add a penalty to the objective function. This is what the rationale behind this last method is. We will just look at some discussion along this line, and then we will move to the linear programming. So you can see that variable elimination, as name itself suggests, it eliminates some of the variables using constraint equations. It is applicable only when constraints are simple. So whenever, let's say, we are having the objective function I is given as x1, which is a function of x1 x2 all the way to xn. A simple example is, let's say, if I am looking at the surface area of a cylindrical container, isn't it? So that will be related to the height and the radius, isn't it? Which we have seen. Let's say I will go back to the same example which is we have started with. Let's say the same example, isn't it? So we wanted to minimize the total surface area. Let's say, so what will be the total surface area? This pi r square, that becomes 2 pi r square, and the other area will be 2 pi r h, which is nothing but the lateral surface area. So this total surface area I wanted to minimize, let's say. Why? Because the amount of sheet metal required is related to the area. So total surface area I wanted to minimize. So in this case, you can see that there are two variables, r and h. But let's say if I am having a constraint, and that constraint says that my volume should be 100 pi meter cube, so I can replace h in terms of 100 by r square. So my two variable problem, see, in this case also we have replaced, see, initially this c was in terms of both r and h, isn't it? But this h I have replaced. So whenever I am having a simple constant equation, I can use this constant equation to replace some of the variables. So initially my c was a function of r and h, but after substituting this h equals to 100 by r square, my c is only function of r. So we can eliminate some of the variables using this method. This particular methodology is referred as variable elimination. So this is referred as variable elimination, and this particular methodology is applicable whenever the constraints are very simple. But let's say if you are looking at large number of uh, uh, constants and these are non-linear in nature, in such cases replacing this particular some of the variables by using these constants is not easy, isn't it? So basically what we do in a variable elimination, these constants are embedded directly in the objective function by replacing some of the variable, and therefore my objective function is a function of now x1 x2 all the way to xn minus k. So you can see that the number of variables are reduced here. Earlier the variables were xn. The same thing happened in the cylindrical container design problem. There also initially we had two variables r and h we have replaced. So finally my objective function became only a function of r itself, isn't it? So you can see that the constant optimization problem is converted to an unconstant optimization problem here in the variable elimination. But this is applicable whenever the constraints are simple. But let's say my constraints are equality, but they are complex and it is not easy to use them for replacing the variable. In such cases, what we do is, in such cases we use Lagrange multiplier. What this Lagrange multiplier method does, it converts this constant optimization problem to an unconstant optimization problem in terms of Lagrange variable. So here you can see that instead of minimizing I, now we are minimizing L, where L is nothing but the Lagrange function, which is a function of x and v, where v is nothing but what? v1, v2, v3 all the way to vk. All these v's are nothing but Lagrange multipliers. So you can see that all these equality constants are multiplied with the corresponding Lagrange multiplier, and these are subtracted from the objective function ix, and this modified objective function is solved, which we call it as a Lagrange function. We can prove mathematically that this particular modification is indeed makes sense, primarily because when you are having a non-linear constant equation, you will see that the point at which your constant and your objective contour satisfy, this is the particular point which is the optimum point, isn't it? At this optimum point you will see that the gradient of the constant and the gradient of the objective both are same, both are having the same direction. They can differ in the magnitude, and that magnitude we refer as a Lagrange multiplier. So if you look at what these v1, v2, v3, vk are, these are nothing but their physical significance is nothing but how much change in the objective function takes place when there is a change in the constraint, and that ratio is defined as v. So v1, v2, v3, vk, all these Lagrange multipliers are with respect to different constants h1, h2, h3 all the way to hk. So v1 in this case will be nothing but what? v1 will be nothing but dou I by dou h1, that is v1. Okay. So Lagrange multiplier can convert this constant optimization problem to a unconstant optimization problem, and once we have converted to unconstant optimization problem, then the same optimization methods which we have seen so far, like Newton's method or gradient descent method, that we can apply here. The only thing here will be, now we will be having more number of variables. In addition to x, we will also have v, isn't it? So the condition of optimality will be what? Dou L by dou x should be equals to dou L by dou v, and all these should be equals to 0, isn't it? The third method is a Kuhn-Tucker multiplier. So in a Kuhn-Tucker method, so remember in a Lagrange method, Lagrange multiplier method, we can only handle the equality constants. But very often in a practical applications like flowsheet optimization or a process design optimization, typically we have inequality constants, isn't it? So whenever we have an inequality constant, we have to go for another method which is called as a Kuhn-Tucker multiplier. So in Kuhn-Tucker multiplier, what we do is we formulate a Lagrange function in a similar way, isn't it? So L here will be function of x, v and u. Here v are nothing but the Lagrange multipliers and u are nothing but the Kuhn-Tucker multipliers. So you can see that here u1, u2, u3 all the way to uj, these are nothing but the Kuhn-Tucker multipliers corresponding to g1, g2, g3 all the way to gj, and you can see that all these g's are nothing but what? Inequality constants. So even these inequality constants and equality constants both are combined here in the Lagrange function. Once we have obtained this Lagrange function is optimized in terms of x and v by differentiating it with respect to x and v, isn't it? So dou L by dou x is equals to dou L by dou v equals to 0. So these are the optimization with respect to x and v. In addition to that, there is a one more additional condition which comes into the picture, which is called as special Kuhn-Tucker condition. And this special Kuhn-Tucker condition is nothing but what? Uj gj x equals to 0. So either this Lagrange multiplier uj is 0 or gj is 0. When uj is 0, what it means is the optimum solution is inside the feasible region. It is not exactly at the constant boundary. And when gj is 0 means it's a equality constant, isn't it? Whenever gj(x) equals to 0, it becomes a equality constant. So whenever gj(x) equals to 0, that means what? The solution, optimum solution, is exactly lying on the constant boundary. So both these conditions, when the optimum solution is lying at the constant boundary or inside the feasible region, both are represented by using the special Kuhn-Tucker condition. And the special Kuhn-Tucker condition can also be derived easily by adding a slack variable here and making it equality, and then doing the same analysis what we are doing in a Lagrange multiplier. With the same condition, we can derive this special Kuhn-Tucker condition, and you can see that all these differentiation dou L by dou X is going to give you one multiple equations. In this case, X is what? X1, X2, all the way to Xn. We will get n equations. Similarly, dou L by dou V dou L by dou V are going to give you all the equality constants, isn't it? Again, this special Kuhn-Tucker condition is going to give you some more equations, and all these equations has to be solved simultaneously, isn't it? And all these equations can be solved simultaneously by using the solvers based on Newton's method. There are typical solvers like sequential quadratic programming. Sequential quadratic programming is commonly used as a solver for such non-linear equations, isn't it? The sequential quadratic programming is actually the extended version of Newton's method. Okay. All right. Now the last method for handling the constant violation is a penalty function. So unlike the previous three cases where whenever there is a constant violation, we were kind of incorporating those constants direct in the objective function, isn't it? So there is no constant violation taking place. Whenever we are generating any solution will be satisfying all the constants a priori. That is what happens in the mathematical substitution method. But unlike that, in a penalty function method, what we do is we calculate the constant hk and gj, we calculate, and whenever we are calculating these values, we check whether these calculated constant values are satisfying or not. Whenever these constant values are not satisfying, then we are adding the penalties, isn't it? So there are two types of penalties are there. One is the hard penalty. Whenever there is a constant violation, we are going to add a large number, a very large number as a penalty here in the function directly, isn't it? Which is called as a hard penalty. And there is something called as a bracketed penalty. So bracketed penalty does what? It calculates the weight, it calculates the how much is the amount of constant violation is there. So extent of constant violation is calculated by using these particular equations. You can see that hk should be equals to capital Hk. Let's say if it is not equals to capital Hk, 1 minus small hk divided by capital Hk, this gives you the fraction of the constant violation you are having. Square of that is multiplied to the large number. So you can see that the extent of constant violation is included when we are looking at the bracketed penalty. And whenever there is no constant violation, the value of pk is just equals to 0. So you can see that hard penalty makes sure that your constant is satisfied all the time, but then it makes your algorithm blind. But when you are having a bracketed penalty gives some intelligence to your algorithm, but satisfying the constant exactly is sometimes not possible using the bracketed penalty, because whenever a very small constant violation is there, 1 minus hk divided by capital Hk, this particular term is going to be very small, and this very small number is multiplied to very large number, that becomes a small number, isn't it? And in such cases you will see that the value of this penalty becomes same order of the objective function, and therefore the algorithm is not going to recognize whether the constraint is violated or not. Okay, so you can see that this particular penalty, which is called as a bracketed penalty, it gives the intelligence to your algorithm, primarily because whenever you are solving a particular problem and whatever the objective function values you have obtained, based on these objective values you can clearly see that how far you are from the constraint violation, isn't it? So that type of intelligence is built through this bracketed penalty. However, satisfying the constraint exactly is not possible. Hard penalty, you will always satisfy all your constraints, but the problem is it is going to make your algorithm blind. Even if you are, let's say the constant of the volume is 100 meter cube, if you are having 100.01, even that particular point is a constant violation for a hard penalty. So clearly hard penalty is going to make your algorithm blind. Even though you are exactly at the boundary, slightly above the boundary, still it is going to consider that there is a constant violation. So clearly whenever you are having a very large number of constraints and you are using a hard penalty, your algorithm typically is not able to converge. So whenever large number of constraints are there, the usual way of handling such large number of constraints is use a bracketed penalty instead of using a hard penalty. So unlike variable elimination, Lagrange multiplier and KKT multiplier which satisfy the constraints a priori, penalty function may start with constant violation which is eliminated over multiple iterations. Hard penalty gives strict constraint satisfaction but do not add any intelligence to the algorithm. In bracketed penalty, penalty is proportional to the extent of constant violation, thus it gives intelligence to the algorithm but it does not lead to the strict constraint satisfaction. That is what I have said initially. Now let's extend our discussion on linear programming. Remember when we started looking at the preliminary flowsheet design, in preliminary flowsheet design what we said is we are going to develop the linear mass balance and energy balance, isn't it? And this linear mass and energy balance we are going to solve so that we can get the preliminary estimate. But even in that particular case you can see that we got almost 100 equations. Now solving 100 linear equations, solving 100 linear equations, we require some systematic way of solving these 100 linear equations, isn't it? So there comes this methodology which we call it as a linear programming. So linear programming is an extremely popular optimization procedure for solving variety of problems in industry, business, defense, which involves linear formulation. Linear formulations are particularly the class of optimization problems where objective function is linear and also your constraints are also linear. Okay, whenever constraints and objective function both are linear, our objective function is referred as linear program. So linear formulations by their nature can be solved very efficiently in polynomial time complexity. This is very important. So whenever we are having the set of linear equations, we can solve this set of linear equations in a polynomial time complexity. That means what? If the size of the problem increases, my time of solving is going to increase polynomially. It is not going to be exponential. There are two types of terms are popular, which is exponential time complexity and another one is a polynomial time complexity. What this polynomial time complexity means is if the size of the problem is increases, then the time required for solving a given problem is going to increase polynomially, this size, not exponentially. Okay, so why linear programming is a polynomial time complex? Primarily because in linear programming we need to only look at the corner solutions. We don't need to look at all the feasible solutions. We only have to analyze number of corner solution, and optimum is lying, definitely lying, necessarily lying at one of the corner points, and all these corner points are finite in number. We can enumerate these corner points in the linear program, and therefore linear programming formulation can be solved in a polynomial time complexity. However, when we look at the integer linear programming or mixed integer non-linear programming or mixed integer linear programming, in all these formulation you will see that solution does not lie at the corner point, and you will have to search each and every point in the search space, and therefore integer linear programming is actually exponential time complex. Mixed integer non-linear programming can become can have a time complexity between polynomial to exponential, isn't it? And similarly non-linear programming can also have a exponential time complexity. So one of the very first methods solving this problem is a graphical method, but most popularly used method for linear programming is a simplex method. We will only discuss this, we will not look at detail of the simplex method, but we will look at the linear programming graphical method so that we can understand the concept little bit more. So let's take a simple example here. A company has two types of toy machines, type 1 and type 2, to produce particular plastic toy. given condition is that at least 3000 pieces of be produced per 8-hour day. A type 1 machine can produce 25 toys per hour with 98%. uh, this number indicates the average number of sellable toys produced. Okay, so 98% accuracy is there for type 1 machine, whereas type 2 machine can produce 20 toys per hour with 95% accuracy. The operating cost of a type 1 machine is 6 rupees per hour, while that for type 2 machine is 5 rupees per hour. Each time a faulty toy is produced, the cost to the company is 4 rupees. The company has 10 type 1 machine and 12 type 2 machines available for production. The company wants to determine optimal assignment of the machines that will minimize the total cost for the production. So now in this case you can see, let's formulate the problem here. So in this case, let's say x1 and x2 be the number of type 1 and type 2 machines assigned for the production, isn't it? Since the number of type 1 and type 2 machines, maximum number possible is what? Type 1 machines are maximum 10 machines are available, type 1, and type 2 machines are 12. So x1 should be less than equals to 10 and x2 should be less than equals to 12. Again, every day we wanted to produce 3000 pieces, isn't it? And you can see that a type 1 machine is producing 25 toys per hour, isn't it? Correct. So 25 into 8 hour shift is there. So 25 into 8 multiplied by number of type 1 machines we are having x1. So that means number of toys are produced by machine 1. Similarly, 8 is the number of hours multiplied by 20 toys are produced by type 2 machine. So 8 into 20 into number of type 2 machine x2, that gives you the number of toys produced by machine 2, and this sum should be greater than equals to 3000 because minimum 3000 pieces we wanted to produce. So if we simplify this particular equation, what we get is 200 x1 plus 160 x2 should be greater than equals to 3000. If we further simplify, what we get is 5x1 plus 4x2 should be greater than equals to 75. Now let us look at the cost calculations. So in this case you can see that for producing each faulty toy, whenever each faulty toy is produced, 4 rupees is the cost incurred, isn't it, for a type 1 machine. So if you look at the type 1 machine, what is the production, what is the cost? Type 1 machine is 6 rupees per hour is the operating cost, isn't it? So 6 rupees per hour is the operating cost plus cost incurred for producing a faulty toys. So type 1 machine is having 98% accuracy, means 2% toys are produced faulty, isn't it? So 2% faulty toys are produced. So with that, so 4 rupees is required for one toy. 25 toys are produced in every hour, isn't it? So 25 multiplied by 0.02. So the production cost for the type 1 machine is 8 rupees per hour. Similarly, we can calculate the production cost for the type 2 machine. Type 2 machine is having the 95% accuracy, and the operating cost for the type 2 machine is 5 rupees. So 5 plus 4 into 20 into 0.05, that comes around 9 rupees per hour, isn't it? Correct. And now we can formulate the objective function for the operating cost. So operating cost in this case will be what? So 8 rupees per hour is for type 1 machine, and how many type 1 machines we are operating? Let's say x1, isn't it? And similarly 9 rupees per hour is the operating cost for the type 2 machine, multiplied by the number of type 2 machines we have used here is x2, and both these are operating for 8 hours, so multiplied by 8. So we get the objective function f is equals to 64x1 plus 72x2, and this we wanted to minimize. So my linear programming formulation is represented like this: minimize f, which is given as 64x1 plus 72x2 subjected to 5x1 plus 4x2 should be greater than 75. This is the linear constant which we have obtained here, isn't it? And these additional two constants which are there, which are bounds, x1 is less than 10, less than equals to 10, x2 is less than equals to 10. And if we are assuming that, this is very important, if we are assuming that x1 and x2 both are a continuous variables, clearly x1 and x2 are the number of machines, but just for a simplicity, if we assume that x1 and x2 are the continuous variable, then this entire problem becomes a linear programming, because all your variables are continuous variables, your objective function is linear, and your constants are also linear, then it becomes linear programming. But in a real practical case, you can see that x1 and x2 are what? These are integer values. This cannot be a continuous. This machine cannot be 1.5. Machine can be either 1 or 2, isn't it? So if we impose additional constraint that x1 and x2 should be integer instead of continuous variables, in that case this particular problem becomes integer program. And let's say this linear constant we had here, 5x1 plus 4x2 greater than equals to 75. If I replace this linear constant by some arbitrary new non-linear constant like 3.7x1 minus 0.16x1 square plus x2 greater than equals to 27.25, I have replaced this first constant by another non-linear constant arbitrarily. In that case, our objective function becomes, our problem formulation becomes non-linear program. Now let us look at the solution of these three programs and understand what is the complexity here in solving each of these. So when we solve a linear programming formulation, you can see that I can draw the feasible regions directly here, isn't it? So in this case, you can see that x1 less than equals to 10. So at x1 equals to 10, I can draw a line which is having x1 equals to 10. So this particular line is going to be this x1 equals to 10. So anything on the left hand side of this x1 equals to 10 is the feasible, isn't it? Similarly, when I am saying x2 is less than equals to 12, so I can draw a line at x2 equals to 12. So and anything less than that will be the feasible region. So this is the x2 equals to 12, and anything below this is the feasible region, isn't it? And the third constraint is 5x1 plus 4x2 equals to 7 greater than equals to 75, isn't it? So in this case, if I put x1 equals to 0, I can calculate x2. So x2 will be nothing but what? 75 by 4. So 75 by 4, if I do, we get this particular point 18.75, isn't it? This is the third point we are going to get, isn't it? So 18.75 is the third point which we are going to get, isn't it? Similarly, if you put x2 equals to 0 and put 5x1 equals to 75, we can get x1. So x1 comes out to be 75 divided by 5, that becomes 15. So we can find out these 2 points by using, we can find out these 2 points. This is 18.75, correct, and this particular point is 15, and we can connect these 2 points by a straight line, and anything above this particular line, is a feasible region. And if you look at all these three constraints, this is the shaded area, which is what? Nothing but the feasible region is. So my optimum solution has to be between this shaded area, correct. Now what is the objective function given here? My objective function is a linear equation which is given as 64x1 plus 72x2. So this is going to give me a straight line, isn't it? So for a, whatever the value of x1 and x2 I can put, I will get some value of f, isn't it? And I can draw a locus of these values of f. I will get the locus of these values of f for a different values of x1 and x2. That will be straight line, isn't it? So I can draw different straight lines like this for different f, isn't it? Now I have to find out that particular point where these straight lines are intersecting this feasible region, and also gives me the minimum value. You can see that as I reduce the value of f, as I reduce the value of f, I am getting different straight lines for the objective function. This is for 1990, this particular line is for 1504, this particular line is for 12096, this particular line is for 1090, isn't it? So clearly you can see that this is the point, at which I am getting the function value f, which is minimum equals to 1090. And how we can find out? I just have to look at these three corner points. You can see that in a linear programming, optimum solution has to necessarily lie at the corner points. So in this case, only these three corner points I have to select. Only these three corner points I have to check. You can see that in this case, this is the optimum solution, which is corresponding to type 1 machine equals to 10 and type 2 machine equals to 6.25. This is the solution of linear programming. We have not imposed here that the number of machines should be integer values. So you can see that we can solve the linear programming formulation much more easily, primarily because we can identify the corner solutions easily, isn't it? We can enumerate all these corner solutions, isn't it? Now simplex method, remember I said that the simplex method is the popular method used for solving the linear programming. What this simplex method does, simplex method is going to start with one corner point and it is going to move from one corner point to the another corner point such that the objective value improves. So eventually you will see that the simplex method is going to sample only the corner points, isn't it? And also in that it is going to sample only those corner points at which your objective value is improving, and eventually you are reaching to the optimum solution. So clearly you can see that the simplex algorithm given by the Danjing is going to solve the linear programming formulation in a polynomial time, and that is the reason why simplex algorithm is extremely popular in the industry. So all these linear programming solvers, they are actually using the simplex algorithm. Okay, so in addition to this linear programming, let's look at slightly more complex case. Now slightly more complex case is what? Integer linear programming. Remember we said that x1 and x2 are integer variables. X1 and x2 are the type 1 and type 2 machines. This cannot be a continuous variables, isn't it? These are the integers. So when we impose that x1 and x2 are the integers, in that case my problem formulation becomes integer linear program, because my variables are now integer variables. So whenever we have integer linear programming, we get exponential time complexity. Linear programming is a polynomial time complex, but integer linear programming is exponential time complex, and that we can see here. See, when we are imposing that x1 and x2 should be integer, in that case we have to only look at the points with only the, so you can see that we can draw a grid here, and this grid should satisfy what? This grid should satisfy the integer condition of the variables. So you can see that I have drawn the grid where all these points are satisfying the integer requirements. So you can see that this is the optimum solution which we have obtained. This is the optimum solution which we have obtained by solving the linear programming. But when we are imposing this additional constraint that x1 and x2 should be integer, my optimum solution is this point D, at which I am getting D type 1 machine equals to 10 and type 2 machine equals to 7, and you can see that at this particular point my objective function value is 1144. Now the important point to note down here is this optimum solution is not lying at the corner. In fact, this can be anywhere in the subspace. In this particular case, it happens to come at this constant boundary here. It is not the corner solution, but it is still at the constant boundary. It's not necessary. It is not necessary. In integer programming, you have to search large number of solutions which are satisfying the integer requirement, and therefore all these number of solutions which are satisfying this integer requirement, this increases exponentially when the size of the problem increases, and therefore integer linear programming becomes exponential time complex. So unlike linear programming where you are only selecting the corner point, in integer linear programming you have to see all the solutions which are satisfying this integer requirement, and number of solutions which are satisfying this integer requirement increases exponentially with the size of the problem, and therefore integer linear programming becomes exponential time complex. Okay, the typical methods used for solving integer linear programming are what? The typical method used for solving integer linear programming is Gomori's integer cut method. This is the popularly used method. Another method is branch and bound. These are the methods which are used for solving integer linear programming. Now let's look at the third case, which is the non-linear programming. So now remember we said that we have replaced the linear constraint. Remember earlier we had a linear constraint which is this 5x1 plus 4x2 should be greater than equals to 75. That was the linear constraint. Now this linear constraint we are replacing by a non-linear constraint. But while replacing, we are making sure that this starting point here and this ending point here both are same. We are maintaining these 2 points same, and within that a non-linear curve we have drawn, and that non-linear curve is having this particular equation. Now with this particular equation you can see that the starting points are same. Now let us find out the optimum solution. So optimum solution, this is the point which we have obtained earlier, which is having function value equals to 1090, isn't it? But when we are having a non-linear constant like this, you can see that my optimum solution is here. It's not at the corner point. In fact, in non-linear programming, my optimum solution can be even inside the feasible region. It can be even inside the feasible region. Okay. So whenever I am having a non-linear programming, my optimum solution can be inside the feasible region, and therefore all the feasible solutions we have to check, and therefore non-linear programming can become exponentially time complex. Unlike the linear programming, which is polynomial time complex, non-linear programming is between polynomial complexity to exponential time complexity. So now we can clearly conclude that whenever the problem formulation is linear, we can solve it easily. Whenever the problem is involving integer variables, it becomes difficult to solve, and whenever the non-linearity is again added, it becomes even further difficult, isn't it? So you can see that the most easier formulation to solve is a LP, then NLP, then MINLP, then NLP and MILP, and the ILP, integer linear programming. These are the problem formulations which are difficult to solve. Okay. And typically the methods used for solving these are all these integer variable problems. Solving the integer variable problems are the Gomori's cut method and branch and bound. For non-linear problem formulation, we typically use the sequential quadratic programming and generalized reduced gradient method. Okay. And for integer programming, for linear programming, we use simplex method and the other interior point methods. These are used for solving the linear programming formulation. So just to summarize this, simplex algorithm is used simplex algorithm is used for solving the linear programming. So this algorithm search only the corner points, the feasible regions selectively, improving the objective function. It requires starting feasible solution which is readily available for formulation with inequality constants. So whenever we have the inequality constants, whenever we have an inequality constant, in that case we use the two-phase simplex method, where one phase is used for obtaining the feasible solution, and then that feasible solution is used in the second phase to solve the usual optimization problem. Okay. The interior point, unlike the simplex method which moves from one corner point to the another corner point, in a interior point method, we start with any of the point at the interior here, and then we move along the direction of the gradient, and the direction of the gradient descent is used for finding the optimum solution. So there are several methods are there in interior point method, like there is a Karmarkar's algorithm is there. There are several other interior point methods. Affine scaling algorithm is there. So all these interior point methods are based on the gradient descent, and gradient descent used for moving a solution point which is inside the feasible region. And you can see that in the interior point method, you will not get the exact optimum solution. You will be approaching to the optimum solution primarily because it moves from the interior of the feasible region. So unlike that, in a simplex method, you move from corner point to the corner point. So therefore, you get the exact optimum solution. The next point is a duality. So sometimes what happens is the problem formulation in one form is difficult to solve. So for every linear programming formulation, there exists another parallel problem which we call it as a dual, and the optimum solution of both primal and dual is same. So instead of solving a problem in a primal form, we solve it in a dual form, when the solution of the problem is easier in the dual form. Okay. And the last one is the special quadratic programming. So special quadratic programming is, so very often our objective function is quadratic and the constants are linear. In that case, even though the problem formulation is non-linear, but same simplex algorithm can be used for solving such quadratic programming problems by adding some additional constants. So that is called as special quadratic programming. So this is the modified form of the simplex algorithm. And whenever we are having the problem formulations like integer linear programming or mixed integer linear programming and mixed integer non-linear programming, Typically the algorithms used are branch and bound algorithm, Gomori's cutting plane method for integer linear programming, and uh, uh, mixed integer linear programming, and MINLP. But whenever we are having only the non-linear programming, in non-linear programming typically we use a quadratic programming. Quadratic programming is the extension of what? Extension of Newton's method. So you can see that this is the objective function, these are the constants. We can formulate a Lagrange function like this, and this Lagrange function is then solved using the same concept of Newton's method. So you can see that these are the optimum values of x and v, which are obtained at k plus 1th iteration. We can obtain that from the current kth iteration values by subtracting the inverse of the Hessian matrix multiplied by gradient, isn't it? So same concept of Newton's method is extended in a sequential quadratic programming. So here you can see that we can do this calculation sequentially for several iterations till we get the optimum solution. Now let's look at the last concept of today's class. Last concept is a multi-objective optimization. Typically when we are doing the optimization of the process uh, process application, flowsheet optimization, or even the optimization of individual units, typically individual units have multiple objectives present. For instance, let's say if these three reactions are occurring, these are the three parallel reactions are occurring in a mixed flow reactor. So R is reacting to produce S in the zero order reaction, R is reacting to produce T in the first order reaction, and R is reacting to produce U in a second order reaction. Now here this second reaction is the desired reaction, whereas the other two reactions are undesired reaction. Now the reactions are occurring in a mixed flow reactor, isn't it? So here you can see that the rate constants are also given. So K naught is given as 0.025, K the rate of production of T is given as K1 CR, that is given as, here the rate constant K1 is given as 0.2 minutes inverse, and the last one is the undesired side product, which is the rate of that is given as K2 CR square, and K2 is given as 0.4 liter per mole per minute, isn't it? Now in this particular case, my initial concentration of R is Cr naught is equals to 1 mole per minute, and the flow rate is V is equals to 100 liters per minute. Okay, now here my objective is to maximize instantaneous fractional yield, instantaneous fractional yield of T. So instantaneous fractional yield of T is defined as I1, that I wanted to maximize. It is a function of concentration of R, which will be there, outlet concentration of R in the mixed flow reactor, isn't it? So max I1, which is a function of Cr, which is given as what? It is given as K1 Cr. K1 Cr is the desired, divided by all other productions. So that is K naught plus K1 Cr plus K2 Cr square. So this is nothing but the instantaneous production of instantaneous fractional yield of T, isn't it? So that is what I am trying to maximize. Now in addition to that, I am interested in minimizing the volume of the mixed flow reactor. So volume of the mixed flow reactor is given as, V is given as, capital V is given as this flow rate V, small v, into Cr naught minus Cr divided by minus Rr. So rate of reaction R, isn't it? So we can represent all these variables here. So that comes out to be 100 into 1 minus Cr divided by 0.025 plus 0.2 Cr plus 0.4 Cr square. So both these objectives we wanted to optimize simultaneously. So first objective is to maximize, whereas the second objective is to minimize the volume, isn't it? And both these objectives are conflicting. So when we solve this particular problem, a typical Pareto optimal front we obtain is given by this. You can see that as the volume of the mixed flow reactor is increasing, my instantaneous fractional yield of the desired product is also increasing. So you can see that in order to get the higher amount of fractional yield, I need to use the higher value of the mixed flow reactor, higher volume of the mixed flow reactor, isn't it? So you can see that all these points in this particular curve are equally good, and these are referred as non-dominated solutions or Pareto optimal solutions. So based on the design requirement, I can select one of the operating solution out of these all equally good solutions, isn't it? So I may use this particular point at which I am getting the fractional yield reasonably high with around 200 meter cube of the volume, isn't it? Correct. If I go here, you can see that I am getting the volume around 750, isn't it? So very large volume is required here, so that will incur a large cost. But if I operate at this particular point, my volume is around 200, and with respect to that I am getting a reasonable value of the instantaneous fractional yield. So clearly getting such trade-off is very important, because once we get such trade-off, we can select a desired operating solution, isn't it? And based on that we can go ahead. So one can see that multi-objective optimization is now is required in all the process application, primarily because we have multiple objectives which are naturally present. Typically, if we are having multiple objectives, we get a set of equally good solution, and this set of equally good solution we call it as a Pareto optimal solution. In this Pareto optimal solution, if you look at this particular point, this is a theoretical based point. Remember, these circles are the actual optimal points. But if I calculate a theoretical based point, that means this is the Pareto optimal front which we have obtained when I am minimizing I2 and minimizing I1 both. So in this case, the minimum of I1 corresponding to this point and minimum of I2 is corresponding to this particular point, and both corresponding to both these requirements, this is the point which is theoretical based point, and this theoretical based point we call it as a utopia point. And opposite of that, where we are looking at the theoretical worst point, which is nothing but the nadir point. So this is the nadir point. So you can see that our Pareto optimal front very often is skewed towards this utopia point. Our Pareto optimal front is skewed towards the theoretical based point, which is this point. If you look at the earlier case, in this case, what was the first objective? This fractional yield was maximization, isn't it? And maximization, so that means the best value will be somewhere, the best value of this will be somewhere here, isn't it? Correct. And the volume is minimized, so clearly my utopia point will be here somewhere. Okay. And opposite of that, my nadir point will be here. So this will be u and this will be n. So depending on whether the maximization or minimization we are doing, the location of the utopia point and the nadir point is going to vary. You can see that Pareto optimal front, which is a set of equally good optimal solutions which are obtained in a multi-objective optimization, these are skewed towards the utopia point, and these move away from the nadir point. So what is the advantage of solving the multi-objective optimization? We get multiple solution, and therefore we get the flexibility of selecting the operating solution. It also reveals the best operating region, and based on this given region, then we can select the best operating point, isn't it? So a decision maker gets more choices of selecting the operating point, and one can select the best operating point based on the industrial requirement, isn't it? So clearly, multi-objective optimization gives multiple equally good solutions. These are referred as Pareto optimal solution. When we are looking at a single objective optimization, we typically get one single solution as a optimum solution. Okay. Let's look at another simple example. So this particular example is in this particular example, we wanted to minimize the total surface area, and also we wanted to minimize the lateral surface area. Why? Because total surface area is required because of the sheet metal which is required for making the cylindrical container get minimized is proportional to the surface area. However, the lateral surface area is more critical because of the pressure stability compared to the bottom surface area and the top surface area. Therefore, the lateral surface area is also minimized simultaneously. So in this case, objective 1, in this case the objective 1 is to minimize the total surface area of the cylindrical container, which is nothing but 2 pi x1 in the bracket x1 and x2. So here you can see that x1 is nothing but the radius and x2 is the height, and the second objective function is 2 pi x1 x2, which is nothing but the lateral surface area. So you can see that this surface area is critical for pressure stability, isn't it? So that is why it is minimized separately, whereas the total surface area, this entire surface area is important because this leads to the least amount of sheet metal for the construction. Okay, so both these objectives are equally meaningful. Now how we can solve this? Let's look at individual objectives first. So we can solve the first objective separately, let's say, and then the second objective separately, just to see how the optimum solutions are going to vary if I solve the single objective optimization instead of solving both these objectives simultaneously. We will see how both these objectives can be solved simultaneously as well. So if I solve this total surface area minimization with the bounds that both x1 and x2 are less than equals to 10, and the constant given here is the volume of the container should be equals to 100 meter cube. So with this the constant equation, we can find out x2. So x2 can be obtained as 100 divided by pi x1 square, and we can use this x2 to replace one of the variable in this, isn't it? So by variable elimination, our objective function becomes 2 pi x1 plus x2 was there, so that x2 becomes 100 divided by pi x1 square. After rearranging, what we get is 2 into pi x1 square plus 100 divided by x1. Now this particular objective function I wanted to minimize. So what analytically, how we can minimize? I can differentiate this equation with respect to x1 and equate to 0. If I differentiate it with respect to x1, what we are going to get is 2 pi x1 minus 100 divided by x1 square and equals to 0. x1 optimum comes around 2.51. Similarly, x2 optimum comes around 5.03, isn't it? And if I double differentiate it, we get 2 pi plus 200 divided by x1 cube, and you can see that if I put x1 equals to 2.51 here, I am going to get a positive number. So clearly the obtained optimum is minimum. If I put this x1 and x2 in the original objective function, I can calculate the optimum value of the total surface area, which comes around 118.85. Whereas if I put the same optimum solution in the lateral surface area defined as what? It is defined as 2 pi x1 x2, isn't it? That is I2 is defined as 2 pi x1 x2, isn't it? If I put x1 and x2 in this, I can calculate the lateral surface area equals to 18 meters square. Now let us solve the second single objective optimization. So here lateral surface area is minimized alone. So 2 pi x1 x2 is replaced by 100 by pi x1 square, so that becomes 200 by x1. If I differentiate it with respect to x1, what we get is minus 200 by x1 square. If I equate to 0, we get x1 optimum equals to infinity, isn't it? But since x1 can be maximally only 10 is possible, because limit on x1 is given, that is I can have x1 0 to 10. So maximum value of x1 optimum can be taken as 10. If I put that x1 equals to 10, I can obtain x2 comes out to be 0.32. Again, I can double differentiate this particular equation. We get 400 by x1 cube. I can put x1 optimum equals to 10 here. That is a positive number. So clearly the obtained optimum is minimum. Now I can use this optimum solution in this objective function, and I can calculate what is the objective value. So objective value of the lateral surface area comes around 200, comes around 20 meter square. And if I put this x1 x2 in this original I1, I can calculate total surface area, and that total surface area comes around 648 meter square. Now these are with respect to individual optimization, but let's say both these single objective optimizations, this one and this, both I am solving simultaneously. In that case, I am going to get a Pareto optimal front, where this first corner point A, is nothing but this, and the second corner point is nothing but this point B. So you can see that whenever we are solving a single objective optimization problem, we only get the corner solutions. We don't get the in-between points. So in order to generate this in-between point, we need to have a specialized algorithms which can generate these individual points, and all these points in this curve are equally good. These are referred as non-dominated solution. But if I look at the other point, like a point D, so remember this in this case, this is the utopia point, isn't it? So you can see that this point D is away from this utopia point compared to C. In fact, this C is dominating over D with respect to both these objectives. So clearly point D is not optimum, it is a dominated point, whereas all the points on these curves are non-dominated points. So you can see that typically a goal programming epsilon constraint method, utility function method, and lexicographic approach is used for solving the multi-objective optimization in a conventional way. So these are the conventional multi-objective optimization method. In goal programming, what we do is, whatever the objectives we are having in our mind, let's say there are multiple objectives are there, One, let's say, is a maximization of profit, second one is the maximization of the customer satisfaction, isn't it? So in this case, what we can do is, what is the final goal is there with respect to each objective, isn't it? So deviation from this particular goal, this deviation is summed up in a single objective, and this deviation is collectively minimized in a goal programming. When we are taking the epsilon constraint method, in epsilon constraint method we optimize one objective at a time, and another objective is constrained at a given value, isn't it? In a utility function method, all the objectives we combine in a weighted manner, and then we are going to change the weights individually, and finally we are going to generate the entire Pareto optimal front. In a lexicographic method we rank different objectives based on their utilities. Okay, so let's say I am having three objectives, but objective 1 is the most important to me, so I will rank objective 1 as the first rank, then objective 2, then objective 3. So what I am going to do is, I am going to optimize objective 1 first, and whatever the optimum value I am going to get, that optimum value I am going to constrain for objective 1, and then I am going to optimize objective 2, and similarly I am going to do for objective 3. So you can see that sequentially I am going to optimize with respect to different objectives based on the rank, which is called as lexicographic method. So clearly all these methods you can see that they require, they are going to give you the optimum solution, one optimum solution at a time. So if you want to generate the entire Pareto optimal front, you have to run these algorithms multiple times iteratively, isn't it? But there are some modern day optimization methods are there which can generate the entire Pareto optimal front in one go, and typical algorithm used for that is a genetic algorithm. So genetic algorithm, you can see that the genetic algorithm, which is based on the concept of evolution and genetics. So initially the initial population of the solutions is generated randomly, and this initial population of the solution generated randomly undergo the operations called as tournament selection operation, isn't it? That is going to give you a mating pool, and then the solutions are selected from this mating pool, and they undergo the crossover and mutation operation. These are going to give you a offspring solutions, and these offspring solutions are then, these offspring solutions are then mixed with the parents, and the best solutions are then transferred to the next generation. So in this manner we are going to perform this cycle for several iterations, finally giving you the Pareto optimal solution. So you can see that this particular method is based on the population of the solution. These do not require derivatives, so these are derivative free, and these converge asymptotically to the global optimum solution. And these methods like genetic algorithm, particle swarm, simulated annealing, even gravitational search, all these metaheuristic algorithms, these can handle multi-objective, non-linear and multi-solution formulations easily. Okay, so these are the advantage with respect to this. Here the illustration of the weighted sum method is given. Weighted sum method is a conventional method. You can see that in a weighted sum method, all multiple objectives we can combine in a weighted manner, and again the summation of all these weights should be equals to 1, isn't it? And then we are going to vary these weights, and we are going to solve this individual objective function multiple times in order to generate different Pareto optimal solution. So if you take a simple example of minimization of I1 equals to x1 square, and minimization of I2 equals to 2 minus x1 square, between x1 varying between 0 to 2, then we can combine both these objectives, x1 square and x2 minus x1 square, using weights. So first will be w1, second weight will be 1 minus w1, and if we differentiate this equation with respect to x1, what we are going to get is x1 optimum comes around 2 into 1 minus w1, isn't it? So now I am varying the value of weight 0, 0.2, 0.4, 0.6, 0.8 and 1. You can see that in this case we are going to get different solutions here, and these different solutions are shown here in the Pareto optimal front, isn't it? So just a simple illustration on the weighted sum method to solve the multi-objective optimization is illustrated in this particular example. So we stop here. Thank you so much for attending. The next sessions on this computational process design will be conducted by Professor Hariprasad Kodamana. So thank you so much and good day.